Okay, welcome to this lecture series on basic surveying, and today we will be talking about again module 7, which is labeling and contouring, and today we are in lecture number 3 of that. What we have done so far, particularly in our last lecture, we understood the terms backside and foresight. Why do we balance them? Then we also looked into the various labeling instruments. We had the demonstration with the instrument also. We looked into some more things, for example, the sensitivity of the bubble tube, and as well as if at all there is some problem with the label, the meaning is we see collimation error, non-parallelism error, how to adjust that, physically working with the instrument, how to take care of that. Though we know by balancing backside and foresight, we can eliminate the resulting error. So this is all what we have seen. What we will do today, we will be looking into the actual labeling procedure, which are height of instrument and rise and fall methods. Then we will be looking into some sources of error and one important thing, that is acceptable misclosure error. Finally, what are the types of the labeling? Reciprocal, profile, cross-sectioning and precise. These different kinds of things we will see today. So we will start with our labeling procedures. Labeling procedures means how actually we perform the labeling there in the field. What we have understood so far? We have understood, well, if there is some ground, we keep our label, they stop at these 2 points, and by making a horizontal line of sight, because we can only make a horizontal line of sight, not exactly horizontal because that is affected by the reflection. Using this horizontal line of sight for a small area, we can say horizontal, we determine the readings RA and RB. Then if I know this particular value, the RL of this point, I can compute the RL of this point. So this is what we have understood. But how actually we implement this thing in field? This is important. So this is what we are going to do now. Okay, this is the field here. Now if you look at the slide, over here we have a point called benchmark. Benchmark means we know the RL of this point. Then there are some more points in the ground, A, B, C, D, E. And the job is we want to start from known point for which the RL is known. The units here are in meter, for example. And our job is to determine the RL of A, B, C, D and E. So how actually we should do this exercise? While I am going through this exercise here, please don't bother about this table right now. While we will explain the exercise, we will come back to the table also. Okay. Now the very first thing, in order to begin the exercise, because this is our area, the terrain which we need to label, we need to find the labels of A, B, C, D, E. So we will take a decision, number 1, that where should I keep my label? And while we are taking this decision, okay, I should keep my label here, I know by keeping my label here, I should be able to balance my sides. Okay, if I am taking the back side here and the foresight here, they should be nearly equal. So this is the decision which I have to take. So I take a decision and I decide that, well, the label should be here. Having done that, the next step will be I'll keep a staff at the known point, which is the benchmark. Because this benchmark RL is known to us, so we keep a staff, and next we will label our instrument. Label means we'll set it up, we'll label it so that the line of sight is now horizontal. Once the line of sight is horizontal, we will take a back side. So what I'm writing here, this 50 indicates the RL of the point BM, 50 meter. The BS stands for the back side, which is being taken by the label here, and this 1.0 indicates what we are reading here on this staff. So this is the observation which we take. Well, how do we record it? Now we will come to the table. In my table, we make a table like this. We write station and backside, intermediate side, foresight, and please mind it, right now we are working with the method of height of instrument. Then we have a column height of instrument, then RL reduce level, and finally we write or we make a column for remark. If there are some remarks, we would like to write it here. For example, this station is called BM, and for this BM, the RL of this is known with 50, and I'm writing, well, it's a benchmark, or some more things I can write about this particular station. The moment we have taken this backside, and the backside is 1.0, the meaning is on this staff, the reading is 1.0, so I'm writing this backside reading here now. So far, just don't bother about any of these things, okay? All of these are just blank. Just don't bother about these. We are only bothering about right now, in this empty table, I have filled it only here. So I'm writing this 1.0. Well, next step. Once I know I have taken it 1.0, now can you estimate the height of the instrument? Okay, what is the meaning of height of instrument? Height of instrument means the moment you have labeled it, in your dumpy level, if you rotate it, or in auto level, if you rotate your telescope or line of sight, it will form a plane. So that plane, what is the height of it, or what is the RL of that plane from that reference surface or the datum? This we say height of instrument. So in this case, as you can see in the figure now, that the height of the instrument can be computed as 50 plus 1.0. So that is the height of the instrument. So this is what we'll write next. So after writing this, next I'm writing height of the instrument in this column. Well, I know the height of the instrument means the height of the horizontal plane. Next job is to determine the RL of A. So to determine the RL of A, I will keep my staff at A now. So the staff is kept at A. It may be the same staff which I am using here. The same staff can go here now. So I am keeping this staff here. I am keeping these reading as such because it will help us to understand this in total. Otherwise in field, the staff from benchmark will move to the point A. Now next, having kept this staff at A vertical, we will take the reading. And what I have done in this case, this line doesn't seem to be horizontal, but doesn't matter. I just rotated my level in a horizontal plane, and we know it. Once we rotate the level in a horizontal plane, the line of sight will still be horizontal. So right now I am bisecting the staff at A, and still my line of sight is horizontal. And I take one observation here, and this observation is 0.5. Okay, I read 0.5 here, 0.5. Fine, we'll explain in a moment because we already know what is the meaning of foresight and the backside. We take the backside to a point for which we know the RL. We take the foresight to a point where we want to end our one particular link of the loop. Intermediate site is any intermediate point in between, where we don't want to shift our instrument level. What I'm doing, I'm taking an intermediate site. It's not a foresight yet because I'm not shifting my instrument after taking this site. So we take this intermediate site, and this intermediate site is 0.5, and now you can calculate very well what will be the RL of point A, because we know the height of the instrument, which is 51. So from this 51, I will subtract 0.5, which I am reading there. So that will give me the RL of A. So the RL of A will be 51 minus 0.5, so 50.5. Okay, this is what we are writing here in our table. We write this observation, and as well as now we fill this detail, because all these columns are already filled. All these records here, they have already filled. Well, next our job is to determine the RLs of other points. We shift our staff to B. Let us do it. Well, the staff goes to the B, and after shifting it, again we will take a site at B. Now this site I am saying foresight In a moment we'll understand why it was foresight and why this was intermediate sight. Well, still the line of sight here is horizontal and the reading here on the staff is 1.5 meter. Well, using the same procedure, at B I am taking a foresight. So at B I am taking a foresight. Please mind it, this is the column for foresight. So we are taking a 1.5 which is the foresight at B. Once we have done it, I can now find the RL of B because I know the height of the instrument. So the RL of B can be found height of instrument minus this. So you can compute the RL and this comes out to be 49.5. 51.0 minus 1.5 is 49.5 and we write it here. Okay, still don't get confused, still we have not written anything here. So we have written now this particular value and this is the RL of point B. Well, next job is, because we need to find the RLs of C, D and E also. So here you have to take a decision. The decision is, should we continue from the same level position where the level is? Should we do that or should we shift our level now? Because if I continue from the same level position in this case, as you will see now in the slide, if I still continue taking the observations from the same level position, my back sight and foresights will not be balanced. My foresight is going to be very, very long. So this is not desirable. Number one. Number two, many times if this distance is too large and our level cannot see the staff here, so it is not desirable to have these long lines of sights. So what we would like to do, we'd like to rather change the level. So this level or the instrument is being shifted to some suitable location. So this is what we did. We just found a suitable location and we shifted it here. Well, having done it, I again set the label, means I again make the line of sight horizontal here. Now, do we know the height of the instrument at this stage? No, because we have changed the label and the height of the instrument will change now. So our first job will be to determine the height of the instrument in this location. How to do that? To do that, we'll take a back sight on this point because for this point we know the RL. So this is what we are trying to do now. We will take a back sight. Okay, we have taken a back sight here. One more thing now at this point which is important. This point B we say as turning point or change point. As I have also written here, turning point. This is also called change point because this is where we are changing our level. And at turning point or change point, the sight which is taken is the foresight. While for A is not a turning point. After A, because A is just an intermediate sight. There could be many more intermediate sight anywhere. But this is the point which we are using for further transfer of level. So this is why this is called change point and this is foresight, and again we are taking a sight on this, the back sight. Well, once we have taken the back sight, we know now the height of the instrument. Height of the instrument is RL plus the value here. So our next height of the instrument will be computed because in our table here, we'll write this back sight on B. Okay, please mind it, the back sight on B, and once we have done it, we know the RL of B also. So RL of B plus back sight on B will give me the height of the instrument. So we know the height of the instrument now here. Once we have determined this height of the instrument, what we'll try to do, we'll try to make use of that in order to determine the other elevations. For example, for C. So what we will do, we'll take a sight at C. Let us say the reading here is 2 meter. If it is 2 meter, we know the height of the instrument for C. So I'm writing for C the intermediate sight. We know the height of the instrument. We can compute the RL of C. So RL of C is known. Then for the next point is D. I again feel, well, Let us again take one more intermediate site at D, and this value is 0.2. Now this is intermediate site and 0.2. So using this height of the instrument, you can again find the RL of D. So RL of D 49.8 can be computed. And finally, you want to close your survey at E. So you will keep your staff at E, and again you will take a foresight. You will observe what is the value of the foresight, and using that, using the height of the instrument, so height of the instrument minus the foresight which was taken there at E, we find the RL of E. So the RL of E is computed. So this is how this entire table is complete. We fill the details in this. So right now what I did, as we were working in the field, I kept on computing also. But actually when you actually work in the field, we don't do the computations there. Rather, we just keep recording, as you can see in the slide here, only the backside, intermediate side, foresight, backside, intermediate side, foresight. This is what only we record. Nothing else. The rest of the table or rest of the computations are done later on in the laboratory. Now, while we are doing the computation, we can have some checks whether we are computing correctly or not. So the checks are, number one, first check is sigma foresight minus backside or sigma backside should be 1.7. Now what I am saying here, you sum up the backsides, sum the foresight and find their difference. The difference is 1.7. Why it should be 1.7? You can see it from the figure, as well as because the RL of first point benchmark and the RL of last point, the difference between these two is also 1.7. So this is a check, and this check is actually checking the accuracy of your computations, whether you have done the computations properly or not. Now one thing in this case you will observe, while we are doing this check, we are only including foresight and backside. We didn't include the intermediate side. If by mistake some intermediate side was wrongly computed, no, instead of 50.5 I am writing 51.5. We don't have a check for this in this check. Anyway, we'll see how we can apply that check later on. So this is the method of height of instrument to take the observations in the field as well as to do the computation and finally to record it. Okay, now we will see the next method of taking the observations in the field, or rather recording, how we record it, how we compute it. And this method we say rise and fall method. Basically we are comparing, a point which we have just observed and a point which we are observing now. What is their relative elevation? The point which is the new point, is this going up or going down? So that's the basic philosophy which we do in this table. How do we do that? Again, please don't bother about all these readings here, because we will start one by one. We'll do the computations. Now in this case, the way we make the table, same thing, our stations are written here, backside, intermediate side, foresight, and instead of height of instrument, we write rise and fall, and finally the reduced level. I have not included the final column which should be for remark, but that column will be here. Well, our terrain is same, the same terrain which we just did, and for that terrain we want to determine the RLs of A, B, C, D, E using the rise and fall method. The procedure is same. We'll keep our label here. The job which we are doing in the field, please mind it, the job which we are doing in the field is not a different one. It's the same job. The only difference is how we are recording it. Please mind it. Well, we keep our label, keep our staff, and take our backside. Having done this backside, I will record this backside here, as well as I am recording that this point is benchmark, so this is RL is 50. Next, I take my staff to A, and I take an intermediate side on that. Now, at this point, if the backside is 1.0 and the intermediate side is 0.5, Then what is the relative RL of these 2 points, the benchmark and the A? What is the relative difference between these two? Well, the important thing in this case is we are trying to compare the relative heights of the points. We have taken a backside at benchmark. Now we are taking an intermediate side at point A. Now, by establishing this horizontal plane and by using these two readings, we can very well say whether point A is higher or lower than the benchmark. And also we can say very well how much higher or how much lower. So this is we are seeing here. So if we see here in this case, the benchmark reading was 1.0, intermediate site is 0.5. You can guess it very well that the point A is higher from point benchmark by half a meter. So this is a case like this. If our benchmark is here and over here is A, this is where our instrument is. I'm taking the observations like this. So this is 1 meter, this total, and this is only half a meter. So obviously A is higher than benchmark. So this is how now I know that A is higher. So A has a rise and a rise of 0.5. Well, next I know the RL of benchmark, and I know that A is rising up from benchmark by 0.5, so I can compute the RL of A also, which will be 50 plus 0.5, so this is 50.5. Well, having done that, next what we will do, because we want to determine the RL of B, we will again take a foresight as we have done earlier also, and the foresight in this case is 1.5. So now what we do, the moment I write the foresight here, I am comparing this foresight or the RL of B with the RL of A. So if I compare the RL of B with the RL of A, by making use of these two observations, by comparing them, you can very well say that for B, it is falling down by 1 meter from A, because B is 1.5 meter, A is 0.5 meter. So B is falling down. Okay, so we write this, a fall at B of this value. So if this is so, what I can do, from the RL of A, I can subtract this fall so that I know the RL of B now. So the RL of B can be computed. Well, let us do it. RL of B is computed. Next, we change our instrument. We take it here. We take a backside, because in order to know the RLs of these areas, I need to connect my survey with the previous survey. So I take a backside. Now the backside is 0.5. Okay, the backside I write here 0.5. Next, I take my start to C and take the intermediate side here. So again at this point I can now compare, because I know already the RL of B. I can compare by taking this backside and this intermediate side, whether C is higher or lower than B. Because the observation is, the reading is more, so C is definitely lower. So C has a fall of 1.5 meter from B. So C is lower by 1.5 meter from B. What I can do now, we already knew the RL of B, I can find now the RL of C. So this minus the fall is RL of C. Having done that, we can go similarly for the D point and as well as finally the point E. So what we are doing, we are just comparing these RLs here, and finally we will write all these observations. Now in this case, as we will see in a moment, we can apply some extra checks. What these checks are, we will see now in the slide. Well, the very first check is RL of first point minus RL of last point is 1.7. Okay. Well, we have already done is sigma of backside minus sigma of foresight This is 1.7. We have done it already. One more check that we can do, because we are either rising up or falling down. So the sum of rise and sum of fall, they should also, if you find the difference of these two, that should be same as how much the first point is higher or lower than the last point. So this is what we are doing here. We find sum of rise, sum of fall, and find their difference, and this difference also comes out to be 1.7. So what we have done, we have now, unlike the previous method, the method of high term instrument, we have also now, because in rise and fall, the way we are computing them, we are including the intermediate sites also. So we are applying this correction now, or applying this check to the intermediate sites also. If any of the intermediate site computation is done wrongly, we can have a check here now. So in that respect, this is a better method. Well, finally, one more kind of the error, that is natural error. Means the error due to natural sources. Very first one on this could be the error due to curvature of earth, or maybe the refraction. We have seen this. How does it affect? The second could be, we observe it. There could be winds. Winds means, if there is heavy wind in the field, it is very difficult to keep the staff vertical. Number one. Number two also, sometime it may happen that your instrument may have some vibrations. Okay, because of that, there will be problem. Then finally, the third one, and you can experience this only if you are looking through the telescope. Please do that. Look through the telescope at a staff which is kept at 100 meter, 150 meter, far away. What you will observe, particularly during the summers, because of different layers in atmosphere and their relative movement, the image of this staff appears as if it is shimmering. So it becomes very difficult, if the staff is shimmering, to bisect a point there, and this leads to again some error. Now we have seen all these different kinds of the errors which may occur in leveling, but what we saw only a few of those. There may be various different kinds of sources, and that you will experience more when you are in the field. Now what we will do, we will talk about the types of leveling. Now what is the meaning of types of leveling? Types of leveling means, we have seen the simple way now how the leveling can be done, but actually some categories are there, and we specifically would like to name them. And how do we do leveling in those categories? This is what we are going to discuss now. Okay, in the type of leveling, we will start with the very first one, which is a reciprocal leveling. Well, I will give you a case. The case is, let us say we are in a terrain, as you can see here, and we have a big river here in between. Maybe the width of the river, or between these 2 points, the distance is 500 meter, or maybe 1 kilometer. These 2 points A and B are very far apart, 200, 300, 400, whatever. Then in addition to this, there is a problem now, because we know somehow the RL of A. Okay, so HA is known to us, and we want to determine HB. Well, how to do that? If you are using the split level or the leveling instruments, how to perform this exercise? That we have to see now. We know, in order to eliminate the effect of errors in the instrument, leveling instrument, as well as the zero error we saw for the staff, or also for the curvature error, refraction error, in all these cases, if we balance the backside and foresight, these errors can be eliminated. But balancing backside and foresight here in this case is not possible. So we can't keep our level here in between. So what to do in that case? We can't keep our level here. If I keep my level only on one side, like this, and I take the observation, somewhere here I read, if I take observation A1 and here B1, A1 minus B1 will not give me delta HAB, the difference in elevation between A and B. It will not give me because of the errors. We know that already. Now, how to eliminate that? Well, what we do in this case, first I would like to keep my level here and take the reading at staff at A1, and take the reading at staff at B, which is B1. I take these two readings. Then next, our desire is, as we know, that my surface along which I am taking the observation, this violet one, should be parallel to the mean sea level or our datum. This is what our desire is. But this is not the case. We know it. We try to make the line of sight horizontal. Still it is not horizontal, slightly in some curve. Okay. So basically we are observing along this blue line B1. Ideally I should have seen at C1, while because this violet line is parallel to our datum. So this C1 is the amount of error. Now how can I write it now? So the delta HAB will be A1 minus B1 minus C1, because B1 minus C1, what we are doing, we are applying the correction at C1. We are not applying any correction at A1. Why? Because the staff here is very near to the leveling instrument, and the effect of error due to non-parallelism, the collimation error, curvature, refraction, all this will be very, very insignificant, okay, negligible. That's why we are not applying any correction at A1. So this is how I can write it. But in order to find the answer, I should know the value of C1. What is C1? How to compute it? Either we compute it and then apply the corrections and find this delta HAB, and then using that we can find the RL of B. But applying correction means I should know about the atmosphere in between. What is the kind of the atmosphere here? In between, I should know that. If that is not the case, what we can do now, in that we have, please keep in mind, we have taken this observation and I am writing this as equation 1 here. Okay. Then second, we shift the instrument here, take again a B2 observation here and A2 here. Again in A2, it should have been, the bisection should have been at point here. I should have seen this, I should have read it. But because of the error, I am not reading this, rather I am reading somewhere here at A2. So I should apply in A2 the correction which is equal to C2. So this is what I am trying to do now. What we are doing here, the difference in elevation between A and B, delta HAB, I am writing for this case as A2 minus C2, because whatever I am reading at A2, I am applying correction to that, minus B2. No correction at B2 because the staff at B is very near to the instrument. Well, one thing is very important here. How about the values of C1 and C2? If we are taking, this is important, if we are taking these observations simultaneously. The meaning of simultaneously means I have one level kept at A, another level kept at B, and we are taking the observations simultaneously. So that when I am taking the observations, the atmospheric condition for both these observations is same. In that case, we can very well say that C1 should be equal to C2. These two errors should be same. Okay. So if these two errors should be same, what we can do, I can now easily sum these two, equation 1 and 2. So 2 delta HAB is, we can sum them up, and if you solve it, just simplify it, we will find it, this delta HAB is A1 plus A2 minus B1 plus B2, because we have already discussed that C1 and C2 will cancel out. So we can still determine the difference in elevation between these 2 points by taking the observations A1, A2, B1, B2, means the observations from 2 ends simultaneously. Okay. Now what if our labels, I was using level 1 at A, level B or level 2 at B. If these two levels have different collimation errors, what should we do? What we would like to do? We would like to exchange the levels also, and again repeat it, because we found, for example, delta HAB when the levels were like, if this is point A, point B, this is level 1 and level 2. This is how we had done it. We find it again delta HAB dash for the condition that at A the level is now the second one, we are exchanging them, and at B the level is now 1, and we will find the average of these two values. So this is how we can also accommodate, or rather we can also eliminate the error which may occur because of the non-parallelism of these two levels. So this method of labeling across a wide river or ravine is the reciprocal labeling. Now next method of labeling is profile labeling. Now these are very simple things. More about these you can read in any textbook. But just to understand these, what these are. Profile labeling means if you have a ground and you want to create a profile of this. Profile means for a ground along a distance is D, you want to know how the RL is varying. Now this is the profile. What a typical profile may look like this, how the RL is varying. This profile is very important in many applications. If you are going to lay a road there in that particular terrain, you would like to know, okay, the formation level for the road should be such that the amount of cutting, this is cutting, all blue shaded is cutting, should be equal to amount of filling, all this red shaded is filling. So for a kind of optimum solution, the amount of cutting and amount of filling should be same. How do we know that? We have to construct a road, and before constructing this, we want to fix the formation level of the road. Okay, it should be at this gradient, and we want to ensure that the amount of the filling and amount of the cutting should be same. This answer will get only if we can do a profile along the road. So how do we do that? In order to do it, for that road, okay, that's the road, or the road is going to be constructed here. What we will do for all these various points, or other, let me take this out of here. This is my level. I keep my level, for example, let's say here, and by keeping my staff at various places, okay, what I am doing, I am measuring all these distances. At the same time, I am also taking sides to all these stops. So by doing this and taking this side also to a benchmark here, I can determine the RLs of all these points. So RLs of all these points are known. So if I know RL of all these points, I can easily, because I know the distance also along this, I can plot this profile, and we can use this profile for our application. Well, the second method, or this is just name, is similar to this one, is called cross sectioning. What it is? Now in the case of the profile, we would like to do the profile if we are interested only in a very narrow strip. But if you are interested in a wider strip, okay, a big highway, which is 6 lane, 4 lane or 8 lane kind of highways there, we are interested not only in one line, rather in a broad area. So our aim is, if this is the area for which I want to know the topography, we would like to carry out a profile. How do we do the profile? Well, if I keep my level here, I would like to have a kind of arrangements of points here. Let us say the points are arranged in such a way that these are the points for which I want to determine the RL. Okay, for all these points, our desire is to determine their RLs. So what we will do, in any of these points, I will keep my staff, take the side to it, while I have already bisected a staff which is kept at a benchmark. So using this, I can determine the RL of all these points. So by this method, what we have a carpet of points. So it's not only a single line along which we know the points, rather a carpet of points covering a wide area. So using this, we can compute these volumes of earthwork, amount of filling and cutting, and all these more accurately. Okay, one more type of leveling is precise leveling. Precise leveling means the staff which we are looking at in our last lecture. We said, the least count is 1 centimeter or half a centimeter. These kind of least count or this kind of stuff is not suitable, or that kind of leveling where we are working with that precision is not suitable in some applications. For example, you are interested in laying down the production line in an industry where various instruments are being kept along the production line. The center line of those instruments have to match very well the levels of the instruments, the level of the foundations. These have to be done very accurately. Similarly, maybe you are interested in, seeing the deflection of a bridge or of a dam. Again, you look for something which is very, very precise, more accurate leveling system. This is where we use this precise leveling. Now, in this precise leveling, how it is done, we especially make use of a staff. The staff is graduated in millimeter. When we bisect the staff using the telescope or our level, this is the level. The level is similar, simple level, auto level. We bisect this staff by making this line of sight horizontal. So we are, for example, bisecting it here. So what we can do, we can read the reading as 105 plus something more. Now how much is this something? We can either guess it, but we don't want to guess it here because we want to measure it, because it's a precision leveling. How it is done? This is realized by one more instrument which is fitted in front of the objective lens, and this instrument is called parallel plate micrometer. Now this is here. What it does? Right now we are looking at over here. If I rotate this parallel plate micrometer, okay, what it will do, it will bring this line of sight down, okay, so that I can bisect now the lower full value. So the lower full value here is 105. So while I am doing it, I am rotating this parallel plate micrometer, and this rotation, how much it has rotated, that we observe. We have to rotate it, another system where we can measure how much we have rotated. So how much physical rotation we are giving to it, that we can measure. Now here is an example. It has been rotated by something, and the corresponding value, how much we really rotated it, we are taking that here. So using this, we can measure up to 0.1 millimeter, and then we can further guess, estimate up to 0.01 millimeter. So it is, it depends upon different micrometers or these different precision leveling instruments. This parallel plate micrometer, what kind of instrument it is, what is the final precision that it will give you. Okay, now we know, we have seen the various things in the leveling, we have seen the errors also. So in any case, however careful we are, there will be some errors in our observations. Now is there any way of checking it? Is there any way of saying, well, the kind of the observations which you have taken in the field are acceptable or not? Now how do we do that? I will give you one example. Let us say we start from a point which is benchmark, and we go to point A, and the difference in elevation between these two is 2 meter. Then this is what we are observing. The moment I am writing 2 meter, I mean I have observed the difference in elevation between these 2 points as 2 meter. Next I move to a point B, and this difference is 3 meter. Now I'm also observing the difference between benchmark and B directly. I can do that. I can do the labeling along this BM and A, then A to B, and also BM and B. And what I found that while I do this, I go BM to B, here I was going like this particular value or the difference in elevation between benchmark and the point B is 4.98 meter. What does it indicate? It indicates while we are taking the observations from two routes, one route here, this plus this, I found the RL of this, then second time I am doing it directly here, I am finding RL of this, the RL in both the cases is coming different. Is it possible? There in the ground is a single point. It should have one RL, but we are getting two different values, through this route and through this route. It's not possible. What we say, this kind of thing, generally when we do the labeling, we will start from benchmark, go to various stations. Let's say we reach A, we reach B, and from B we will finally close at benchmark. If I draw it again, in any labeling, this benchmark is here, the various points for which I need to find the labeling or I need to find the RLs. What I would like to do, I would like to go like this in steps and I close it. Now, whatever the value here, H1, H2, these are the difference in elevations, H3, H4, H5 and H6. So, sigma of all these H should be equal to 0 with the proper sign, because I started from a point, I reached the same point and the difference in elevation should be 0. Okay, sum of those differences of elevations. But it will not be so. We know it will not be so, because in individual observations, all these individual ones, they have some error. So now the question will be, can we really say something about this error, whether this error is acceptable or not? We have a way to take this decision. Well, how do we take this decision? We say the acceptable error should be if my delta H, let's say this is the closing error, is less than equal to m k raised to power half, also m n raised to power half. What these are? Here m can have a value from 2 millimeter to 12 millimeter, depending how precision we are looking for. If you are looking for a very, very precise survey, our value will be somewhere here. If our survey is not that precise, our value will be here. Now, what is K and what is N? K is starting from a point, going to the another point, and finally closing our level. This is how we have closed the level. What is the total distance in kilometer? That is K in this formula. And the N stands for, when we are doing this exercise, I might have kept my instrument in several places. How many settings of the instrument? All these are N. So we can use either the kilometer thing or the N, and we have to use the same throughout our entire project. Okay, so this is what the N is, number of the settings of the level instrument, because we know, more is the kilometer, more will be the error, because definitely we cannot be true in our observations. We can never get the true value. There will be some error. Now, if we are doing a very large network, that total error will be more. So this is why it is proportional to K. Similarly, more number of instrument stations means larger is the network, and the number of the instrument stations are more will be the chances of the error. So again, it is proportional to the N. So by knowing how big my network is, we can take a decision whether my error is acceptable or not. Well, the closing error, let's say delta H is the closing error. If it is less than these values, K raised to power half and the other one, we will accept it. Accept means we will say, okay, there is no need to revise the survey, to go to the field again and do the survey. But what we need to do is still our network, within the network, because we are finding the difference in elevation between all these points, and when we find this sigma delta A is the difference, it should be 0. It is not 0, but there in the field it is 0. So what we should do? We should try to adjust our observations. We should apply corrections to our observations in such a way that this becomes 0. Now how do we do it? There is a simple method. As we are distributing the errors, we are distributing the error, or rather we are finding the error, the acceptable error, parallel, proportional to the distance in kilometer or proportional to the number of the settings. Similarly, we will try to eliminate the error also, or to apply the corrections. Well, what is the way? In a network like this, if the closing error is delta H, this is H1, the difference in elevation between 2 points is H1. So for this A and B link, the correction in H1, this will be, what is the length of AB divided by, what is the total length, perimeter, the entire perimeter here, multiplied by the closing error. So we can distribute now, we can find the correction and we will apply this correction to the H1. Similarly, everywhere H2, H3, H4. So this total error has been now distributed. We can also do the same thing. Instead of writing it like this, in terms of, how many stations, how many settings between A and B divided by the total number of the settings in my entire network. Now, as far as our network is a simpler one, just like this, closing, the job is very easy, we can distribute it. But there may be a case when my network is, I have taken these RLs also. So there are not a single closing loop, there are many closing loops. My observations should finally satisfy the closing thing in this loop, or maybe in this loop, or also in this loop. All possible loops which are there, they should be closed. So we cannot adjust now by taking only a single loop. Rather, we have to take all these possible conditions which are existing in my network and then adjust it. And this is what we will see later on when we talk about adjustment and computation. So what we did today, we talked about some special types of labelings, reciprocal, profile, cross-sectioning, precise labeling. We also saw how we record the observations in the field book and how we do the computation by these two methods. And finally, we saw the concept of acceptable misclosure error.